So it looks like we've got a 1 o'clock start. I'm going to go ahead and get started. Welcome to the DCO SOSSEC sponsored Cyber Talk for 2020. My name's Ed Aguirre. I'm with SOSSEC and normally at the Forge at Fort Belvoir, but due to COVID-19, most of the base is working remote. So this event is 100% virtual, and everybody is in their home quarters for this event. So thank you for joining. And I'd like to introduce today's Cyber Talk company, which is Napatech Inc. Incorporated. Speaking for Napatech will be Pete Saunders, who's Vice President of Field Application Engineering. And along with Pete is his colleague, DJ Root, who's a VP of Federal Sales. The title for their event today is Network Capture Hardware. And along with Napatech today, we've got their guest, which is Axellio Inc. and Mark Zeller, who's the Chief Revenue Officer. He'll have some material to go through a little bit after they've started. So some virtual logistics. Everyone has been muted on entry, so if you happen to notice your mic on the right-hand chat area is unmuted, please mute yourselves because we'll pick up whatever's going on in your area. And also, we're encouraging your questions in the chat. So just go ahead and submit those questions. Somewhere about the 15th slide for Napatech, they're going to pause and maybe take a few questions that may be in the chat. But we do want to hold for questions live to the end, where they'll pause and we'll open up you'll unmute yourselves if you have a question. And the guys, the three gentlemen, Pete, DJ, and Mark will take questions, and then I'll close at the end. So at this point, I'll like to turn it over to Pete Saunders of Napatech.
All right, well, thanks a lot, Ed. I hope everybody out there is doing well with this pandemic. I wish the best for everybody. So, what I do for Napatech is I run the field engineering team. And what I'm going to talk to everybody today primarily about is it's more of an educational presentation, but what I'm going to be focusing on is, what is packet capture, what's important about true zero packet loss and packet capture use cases. Whether that's a cybersecurity use case or other use case for packet capture. So that's going to be my focus. I'm going to explain to you how we do it here at Napatech. And then, Mark from Axellio is going to give his presentation, which is going to be a real world example of a solution that his company is working on. So let's just get, and as, like Ed said, if there's any questions, feel free to put them in the chat window. When I get to you around slide 15, I'll see if I can answer them for you. And then we'll have more time at the end to basically do more. So, yeah, so for people on the call that don't know what packet capture is, so essentially what packet capture is the ability to sniff off the network or view or record or capture every single network transaction, right? So every packet in for cybersecurity monitoring devices or for, maybe network performance monitoring, right? So, unless you're monitoring your network, unless you're looking at what's going on your network, you really don't know, right? So whether it's a cybersecurity type monitoring use case or it's, network performance or application performance, you really need to have, full visibility. And so packet capture devices, are not a network endpoint, and what that means is they're not visible to the network, right? So a server client typical configuration, you have a server that talks to a client. Both of those are visible on the network. In the case of a capture device, it's purely passive. Okay, so it's a passive network device that's not visible to any other element on the network. And most use cases, ideally, they would like to be able to capture every single packet or message on the network. And but that doesn't always happen, right? And it's usually a hardware limitation or a software limitation or an architecture limitation. And these devices are usually connected through some special hardware, right? And one is a passive or an active tap. And if you look at this picture here where you see the little tap, basically you've got a switch or router. This could be clients and servers hanging off of these devices. And the point is that a copy of every packet is sent to this packet capture device invisibly. And it's basically, so everything going this direction goes to this device, everything going this direction goes to this device, but it doesn't affect the communication between the switch and router in this case. So that's what a tap does. And there are two different kinds. There's a passive and there's an active tap. A passive tap is typically in fiber networks, and it's an optical passive device, doesn't require any power. And so they just do that by splitting the light. In the case of an active tap, this device here in the middle is actually powered, is active, it has other capabilities that you can get through active processing. The other ways it's deployed is just a switch span port, and that's what this picture is showing here, is that you have a number of different devices communicating through the switch, and then you can see a copy is being made, and it's being sent to this packet capture device here. And for packet brokers, it's very similar. Kind of a similar architecture where you would have. The only difference is the packet broker is kind of purpose designed to take traffic and actually deliver it over many different ports to many different monitoring devices, where a switch span port is really a feature built into the switch. So that's at a really high level. That's what packet capture is. That's what it does. That's how it's implemented. That's how it's deployed. So let's just move on to the next one. So some of the challenges to doing packet capture. So there's many challenges, but in many cases, a standard off-the-shelf server NIC can be used for doing packet capture, but it's really designed for low latency packet by packet delivery, client server communication, one packet at a time. That's really what that hardware is designed to do, and that's where it works perfectly, and for endpoint communications. But there's no guarantee, right, that every packet will be delivered at high traffic loads. Okay, and that's where the protocols on the network are there to do things like retransmission to handle that. And it's not optimized for basically the theoretical limit of the network, right? The smallest frame size is at the highest frame rate. And so, the bottom line is when a standard server NIC is used as a packet capture device, most likely you're going to have some packet loss. And the other thing that is important to many monitoring devices, whether it be cybersecurity or network performance or application performance monitoring, the packet ordering is not, is really important, that the application gets the packets timestamped in the order that they traverse the network. But with a server NIC, there's really no way to do that. You have multiple interfaces, and then the software has to figure out what the order is, and that's not always possible to do for many reasons. But again, the typical client-server communication, that's what a standard off-the-shelf server NIC, like from Intel or Broadcom or others, maybe it's built into your server motherboard, maybe it's an add-on card. The point is that it's designed for communication. It's not designed for packet capture. So it's in-bandwidth communications. And like I said, there's flow control. There's also protocols they'd use to throttle the traffic, and then retransmission is also possible. So it's not a requirement in client-server communications that that there's zero packet loss, because you have these mechanisms there to make up for it. Some of the things that are critical for all packet capture use cases, right? And in these pictures over here, I show this is your typical client server. Here's your server, and there's a client over here that's talking to it. So it's they're two endpoints talking to each other. Here's where we're again out of band monitoring, where this would be a tap, and then this is a dedicated capture appliance or monitoring appliance. It may look like a server, but it's actually doing something very special on the network. So again, the NIC is out of band when you're doing packet capture. It's invisible to the network. It's passive. It's not involved in the network communication, and it's not an endpoint. So again, if that NIC that's doing the packet capture can't keep up with the traffic, well, there's nothing there to prevent it from dropping those packets on the floor. And once they're on the floor, they're gone forever, right? So you can't go back and go, well, I wonder really what happened yesterday at 10 o'clock at night, right? Because you don't, and maybe you have some of the packets for that event that happened, but maybe you don't have all of them. Maybe you don't know, okay? So anyway, that's what that missing packet data means. If you're looking to do some post-mortem analysis on maybe what happened on your network, it's going to be ineffective if you don't know the fact that you don't know if you have all the packet data or not. Same with cybersecurity. Real-time cybersecurity monitoring. It's the same thing. If there's an event that happens on the network, it doesn't get all the packet data, it may not trigger an event. I'll go into that in a little more detail. Okay, but here we have. This slide illustrates, the effect of packet loss on network recording. I'm just moving this chat window around, so I don't know if that's affecting the presentation. But you can see here, this is what a network recorder does. Again, it's sniffing packets off the network through a tap or a span port or packet broker, and it's writing these to disk. Okay, so it's storing them on the appliance itself for later analysis, right? For whatever reason. Again, maybe it's a security type appliance. Maybe it's doing network performance monitoring, looking for network outages, and whatever the monitoring use case is. But the primary value of having the ability to record traffic on your network is that cybersecurity and network engineers can go back in time and retrieve all those packets, all those messages for a given event. So if there's an event that happens on the network at 10 o'clock at night and it happened for 2 minutes, they can go back and retrieve that packet data and then do some in-depth analysis on it. You know, if it's a security breach or again, if maybe it's a performance issue on the network. And so this packet data, like I said, can be used to analyze, you know, these events that happened in the past. And then the other things that, you know, maybe not just to analyze that one event, but many times that packet data for that event is archives. You know, it's, you know, it may be just a few megabytes worth of data, but you archive that for later purposes. Maybe you see that event again in the future, or at some point in the future you have that event again, and then you've got more data that supports that, you know, that case or that event. You know, the biggest problem is, you know, when you don't capture it all, right? And so, you know, you get incomplete or invalid analysis. You can't do a, you know, in-depth, valid analysis without knowing that you have every single message that was involved in that event. So, you know, essentially you end up with an incomplete picture of, you know, how, when, why, you know, that happened. You know, you may have when approximately, but without all the packet data, you may not know the how and why. And determining the root cause just may not be possible in the end if you don't have all the packet data. So that's the negative effect of packet loss in network reporting use cases. Okay, so now we're going to talk more about what an intrusion detection system is, and again, it's a device monitoring, you know, out of band monitoring. It looks like a server in a rack, but what it's doing is it's in real time. It's looking at every packet on the network, and what it's doing is it's applying a set of rules. So there might be 50,000 rules that are being applied for every single transaction on the network, and looking for certain behavior, looking for certain types of activity that may be malicious. And that's what an intrusion detection system does. It looks for network intrusions, right, based on a rule set. And these are some of the open source tools that perform that kind of functionality, Suricata, Snort, and Zeek. And so we work with those open source tools. We're involved in those communities. And in fact, this data here is came from one of the Suricata conferences, actually the one last year. So, but this is really important. You can see that, you know, when you get an event or when the intrusion detection system, the IDS, when it's looking through the rules and it goes, here's an event that matches this rule, what it does is it generates, you know, an alert, which ends up going to your cybersecurity engineer at some point, and they have to look at it and see, is this a real threat or not? You know, the problem with packet loss is that any missed, you know, IDS alerts, you know, basically when you lose packets, so with a 3% packet loss, you miss 10% of the alerts. That's a lot with just 3% packet loss. And when you get up into the, you know, higher numbers like 25%, you know, you're going to miss 50% of your potentially miss 50% of the alerts that an IDS system would generate. You know, that's pretty bad if you're looking for, you know, malicious activity on your network. So this is, again, you know, how just a very small amount of packet loss, like 3%, people will say, well, 3%, and that's 3% could easily happen with just standard NIC hardware that you would use for endpoint communication. But you're going to miss 10% of your alerts. That's not very good. And then here's another use case. You know, what an IDS also has the ability to do is, so if a file is sent over over the network, it has the ability to extract that file from the packet data. So, you know, if somebody, you know, sends an attachment, or it's some malware attachment or something like that, the IDS can actually extract that file, but not if there's a lot of packet loss. But again, even only 4% in this case, they can't extract the file. And then only 5.5%, so you can see it's even worse for file extraction. You have 50% failed extractions with only 5.5% packet loss. So these last three slides I've been discussing are really, you know, three primary factors, right? In you know, how packet loss can affect the accuracy, the quality of your network monitoring. So what I'm going to talk about now a little bit is, so what Napatech, and I'm going to go into a little bit more detail about what Napatech does and what we, and the technology we use under the hood. But essentially what we build is we build specialized NICs. We call them smart NICs, and they have one large device on them essentially, and it's an FPGA, which stands for Field Programmable Gate Array. And what's nice about these types of devices is that they're very flexible, and they can, you know, they can be programmed to do many different things at very high speeds, 100 gigabits. So today we're doing 200 gigabit processing in an FPGA, and which is, you know, that's extremely fast. So, but just here's a quick kind of refresher or a quick introduction on what an FPGA is and how it can be used. But it's essentially a programmable logic device. Okay, so and it essentially contains all these blocks that can be interconnected to perform, you know, all different kinds of functions. And it's chip design, but it's programmable chip design. And so these chips can be reprogrammed unlimited number of times to do all different kinds of tasks. You know, they're used for everything. I'm sure a lot of people are familiar with an FPGA, as they've been around for many years, and companies like Xilinx and Intel make them. So the other really good thing about an FPGA is, so you've got the performance of hardware, of doing the processing in hardware, but you have the flexibility of being able to change the function of that hardware without having to build a new piece of hardware with a different chip or redesign a chip. It's all programmable in the field, and that's why they call it a field programmable gate array. So so again, it's one hardware platform. It can support unlimited use cases, essentially, to do many different things. If you can fit the functionality in the FPGA and make it work at speed, then it's going to address that use case. So that's what an FPGA is, and this is what a smart NIC looks like, and this is the Napatech NT200A02 smart NIC, and it's a COTS device. It's designed to go into off-the-shelf servers. It's designed to be fully PCI compliant, but it's got that large FPGA on it. Okay, it has a Xilinx UltraScale FPGA on it, so it's a very dense, very fast FPGA. It's a PCI Express card. And here's just some of the high-level hardware features, and I'm going to go into a little bit later in the presentation about how these features, you know, address the packet loss challenge, right, that I discussed earlier. But essentially, it's got 12 gigabytes of memory on it for buffering capabilities. It's got a 16-lane PCI Express slot, which basically gives it a full 100 gigabit throughput over the PCI bus. It's 100% compliant, and it's fully, compatible with any off-the-shelf server that's PCI Express compliant. And what it has for these interfaces right here, these are the network. This is the PCI connector. These are the network. I'll get into a little more detail later. But essentially, these types of interfaces support 10, 25, 40, 50 gigabit, 100 gigabit, all through the same hardware and a firmware change. We support other things like 8 ports of 10 gig and 25 gig. It also has very precise time synchronization capabilities, and these cards are used in network latency measurement use cases as well. So when you're doing network performance monitoring or transaction monitoring, you need a high precision timestamp. Again, meets the PCI spec with regards to power. And then the other thing is, so what we provide is the hardware, but we also provide that software that runs in the FPGA and for specific use cases. Excuse me. But it's also available as a blank card if there are expert FPGA developers out there that want to develop their own application of software to run on the FPGA. So let's talk about, so now you know what a smart NIC is. Let me have a sip. You know what an FPGA-based smart NIC is now. So it's a combination of the hardware and the software that, Napatech has the expertise also in the software development side as well as the hardware. So we have the software load that's purposely designed and optimized for packet capture performance, right? So regardless of the network utilization or the packet size, so the worst case scenario is the smallest packet size at the highest network utilization, because that makes the packet rate, that puts the packet rate at its maximum. And most off-the-shelf NICs just can't handle that load, whereas this device, again, it's designed purposely to do that. It can capture everything without any packet drops. Some of the things we do is we do the time stamping in the hardware, and again, that's important for mainly network latency and jitter measurements, but it also gives you an extremely accurate timestamp to the nanosecond or even network events. If you need that resolution, if you need that accuracy, it provides that as well. The other thing that's important is we merge all the packets together into a single stream internally in the FPGA, and what that guarantees is the packet ordering, right? And you remember on the previous slide how important it is for packet ordering, because if packets come out of order, it can basically mask or it can make an IDS drop that whole flow. So packet ordering is extremely important. We do that all in hardware, so it's guaranteed. And then we have the buffering on the card. The 12 gigabytes of buffering gives you the ability to do full packet capture, where the network utilization is high, so microbursts on the network. And also zero packet loss when the PCI bus can be busy for microseconds, and when you're talking about 100 gigabit throughput, a microsecond is a lot of data. We also have large host buffers, and then these are some of the other things that are also utilized. We bypass the operating system kernel. It's all DMA. There's no copying going on, so it's extremely efficient. So the application that's running on the host that's trying to look at all these packets, the last thing we want to do is put a load on that on the CPUs in the host. So these are the things we do to offload it. So we do like a receive side scaling to multiple threads, deduplication, so we can count or discard duplicate packets on the network. So you have the option to capture everything, including all duplicates, but you can also drop them to save disk space or whatever your use case is. We also do some stateful processing as well. We have a software load that allows stateful flow processing. So again, this is kind of the combination of this server platform, our SmartNIC, and our software. And then again, we work with these open source applications, and we're involved in these communities, Suricata, Snort, and Zeek. And so we have many customers that have deployed our packet capture software and our SmartNIC, and you know, and they're running in networks all over the world at 24/7. And so these are the things we can do. We can guarantee the delivery, right? Full throughput, any packet size, 0 packet loss. Minimum of 500 millisecond buffer on the card itself. And then the things that we do is we optimize that PCI Express bandwidth so that for this particular use case, right, which is being able to capture massive amounts of network data. You can imagine at a 100 gigabit network, you know, that's even 50% utilized. That's a lot of data, right? It's a lot of data to process, and without a SmartNIC and an FPGA, you know, the server is just not going to be able to handle it. And these are the things we do. We optimize. We're optimized for Intel Xeon, but we also are working on optimization for the latest AMD platforms that are coming out. And so these are some of the kind of gory details about what we do. But we get the highest CPU cache performance and highest CPU core utilization. So, you know, the bottom line is that, you know, we deliver all this packet data to the host application, whether it be Suricata, Snort, Zeek, or some proprietary application, and we do that with, you know, we do that with very low load on the system. So what slide am I on now? Hold on a second. I see this.
I think you're coming up to 12, Pete.
All right, I'm on 12. Okay.
Yeah.
Okay. Okay. I see there's some questions. That's good. We'll get to those in a minute. So again, here's just a kind of, you know, high-level view of what our FPGA capture software can do. I'm just going to brief some of these I've already gone through. But on top of the capture features that we have, which I've talked about in the previous slides, and we also have flow processing in a separate software load that's designed for capture. And it's also not just about capture as well. It's also the ability to replay traffic. So we can capture traffic at a very high fidelity, right? So with a very precise timestamp, so 1 nanosecond resolution timestamp on every packet, and this is where some of our financial customers actually use that to basically then replay it at a later date to do analysis. So we can capture all that traffic, we can write it to disk very precisely, and then you can actually, you know, replay it kind of like a DVR, right? And replay that packet back out to some other device for like test and measurement type use cases. And we also have a local retransmit feature, which is port forwarding. type functionality, almost like a built-in tap. So you can eliminate a tap or packet broker if you choose to. So these are the high-level features. And then this slide, maybe too much detail for this talk, but I'll go through it quickly for those of you that are interested. But essentially, we have two ports on this particular SmartNIC. Both of these can run up to 100 gigabits. We have a MAC. This is where we do the merging. It's a channel merge. So this is where we merge the data from those two ports in exact time order that they came over the network. And we have an extensive packet decoder inside. You know, a lot of the features, so for people on the call that are familiar with a packet broker, essentially what this is, in a lot of ways, it has other features too, but it has a lot of the same features that you would find in a packet broker. The difference is that it's on the NIC, it's on the SmartNIC. So we can do things like packet decoding, and we can do load distribution instead to different ports. We do it to different CPU cores on the host. So this is the packet decode. We have extensive statistics that do things like count frames, different sizes, CRC errors, drop packets, checksum errors, all those kinds of things that if you're looking for issues on the network, those are the things you want to know. You know, do we have a lot? Do we have corrupt traffic on the network? Flow processing, we have the ability to do filtering and slicing and things like that, and that's what happens in this block. Whoops, sorry. And then we have this buffer system that I talked about with the 12 gigabytes of buffer. So we do all this upfront processing. We put all the packets in a buffer, and then we feed them over the PCI Express interface, which then goes to our, essentially what we call host buffers, which are, buffers in the server host memory that then the applications like Suricata or SnortSeek, any of those can then pull that packet data from those buffers to do processing. And then, like I said before, we have this IEEE 1588 and GPS time synchronization capability as well for certain deployments. They need very high precision synchronization. And again, here's an overview of some of the other use cases that this capture software running on our SmartNIC can apply to. Obviously, cybersecurity, intrusion detection and prevention. We already discussed that. Network recording and replay. We discussed that as well. Subscriber analytics and monitoring. Any kind of monitoring on the network. Test and measurement use cases. So we have companies building test and measurement solutions with our SmartNIC that test networks, test the latency on the network. Network and application performance monitoring. Many of the, Napatech is primarily an OEM, and our technology is under the hood of many appliance manufacturers out there. So if you're familiar with using, I can say IBM, for example, appliances out there that do cybersecurity type use cases. We're in those. Our technology is under the hood. But open source. So like I said, we're involved in these open source projects. We think there's a lot of value for Napatech, but also for these communities where people are trying to build their own solutions. But we also, like I said, we have lots of commercial customers that build their own proprietary applications that run on top of our API. And you can see the logos there for our open source partners, right? T-Rex is a traffic generator open source project from Cisco, And DPDK is a data plane development kit, and that's an Intel initiative, which we're closely involved with as well. So we really support these communities because we think, you know, it's a win-win for everybody. And then just quick overview of, like, I've spent most of the time here today talking about capture. I briefly talked about capture with flow processing, but that's a different software load that we have available for our SmartNICs. And what this does is it does stateful flow processing on the NIC. So essentially it has a huge flow table, 50 million flows. And what it allows is applications to, like an IDS, Suricata, we have a full integration with Suricata. So you can write a Suricata rule and tell Suricata, hey, you know, you ever see this type of traffic? I really don't want to look at it, okay? You can tell Suricata that, and what happens is Suricata then programs down into the Napatech flow table in the FPGA to basically drop that, right? And the reason why you would want to do that is, you know, you probably don't want to be capturing YouTube, but maybe you want to. But if you don't want to, this is how it's done. So this is just one example. But we also have an inline capability as well. What that does is, you know, so we're bumping the wire. We're still invisible to the network, but we're inline. And this type of use case is for what they call intrusion prevention systems, and IPS, and others. You know, firewall use cases. You know, where you maintain a whitelist and blacklist. And that can be downloaded into the flow table on the SmartNIC. So all that happens in the hardware at 100 gigabits per second, full duplex, without packet loss. And so that's, you know, so to be able to do that on a standard COTS piece of hardware is pretty impressive. So that's our inline flow processing. And then lastly is we also have a virtualization software load, and that's focused on Open vSwitch acceleration for SDN, NFV deployments. For those of you that might be familiar with virtualization, it's a very CPU core intensive use case, right? So that switch can utilize more than 50% of the CPU cores or CPU processing you may have in a server. And what we do is we offload that again into the FPGA, into the SmartNIC, so that you can basically deploy more network elements on the same hardware. So that's our virtualization. I'm not going to go into it too much more, but you know, if there are any questions, we'd be happy to take them. So, DJ, I think this is where we're going to stop, right? Maybe answer some questions.
Yeah, no, Pete, there are none thus far, but I think we can keep going.
There's a couple here. There's a question on the FPGA. Did you answer that one? I got another one.
How are IP fragments handled?
Yeah, so I can answer that. So we do have IP fragment support. Today we don't do the full reassembly of those IP fragments, but what we do today is we can sort them into different host buffers to make it easier for the application to do the reassembly. So that is something that we are working on, and at some point we hope to have that capability. In other words, a full reassembly solution, and it may be all in the FPGA. It may be a hybrid solution where some is in the FPGA and some is running in the Napatech host software. but today we do have customers that use our IP fragmentation support, and it's more of an offload. It's more of a coprocessor than a complete reassembly solution.
He's got another one here from John T. Since it is a field programmable device, is there potential for a misconfiguration or malware to be introduced? Excellent question.
Yeah, that's a good question. And so the way it works with an FPGA is first of all, it's a static device. So what that means is when the power is shut off, it loses its program, right? So when you power it off, when you first power on an FPGA, it's just a blank slate. It's all static RAM based. So for those of you that understand the difference between static RAM and dynamic RAM, but it's all static RAM based. So when the device first powers up, what it does is it reads the program out of a local non-volatile RAM, what we call a flash memory. And so that flash memory is, it has a checksum, kind of like you would have a checksum on a file. So the first thing that the FPGA does is verify the checksum on that flash, the contents of the flash. So if the flash was ever corrupt in any way, modified or changed, then it would detect that and it would actually read from the backup flash. So there's two flash devices, a primary and a backup. So that's the way that works. And the other thing to remember is the flash device is not in the data path of the network at all. So it's not in the network data path, and the way it's modified and programmed is proprietary. And lastly, when the SmartNIC is up and running, the flash memory is basically locked, so it can't be modified when it's up and running. The only way it can be modified is it has to go into a maintenance mode. So I know there's a lot of detail there, but hopefully that helps answer the question.
Additional question from Robert R. Would the card be able to run in promiscuous mode and integrate with Nmap or Wireshark? And the follow-up to that, are you able to pull data from the device for reporting? So
yes.
Yes and yes.
Yes, it does. Yeah. So promiscuous mode is, passive, right? Capturing off a tap, like I talked about on the first slide. So yes, it is it's only a promiscuous mode device. Excuse me. When it has the capture software running on it, it's purely promiscuous. There's no stack running. There's no driver in the operating system. Again, we're a purely dedicated packet capture device, right? And that's why we can achieve the performance levels that we can achieve. And the last question, as far as, yeah, so like I said, you can get all the packets, every bit of data off the device without packet loss, but there's also a very extensive monitoring interface from, like statistical interface, number one, that we generate all different types of statistics that you can monitor, and as well as the monitoring of the hardware itself and the environmentals.
Okay, Pete, I think that does it. We're at almost 50 minutes past the hour as a time check. Okay, so I just got a couple more slides here. And again, I kind of already talked about the hardware, so I'm not going to go too much on this slide. The only thing I'll mention is that some of the innovation that Napatech brings to the table is our hardware design.
capabilities, and these devices are extremely robust, extremely rugged. Our failure rate is less than 4.4%. It's typical what you would see. So it's really purposely designed to run 24/7 and give you 100% packet capture 24/7. But here's some of the other, it's got lots of monitoring capabilities. It monitors its own temperature. So it's really a system on a NIC, and it's purpose-built to be very robust. And that's why many of the companies like IBM that build appliances use our product. It's obviously the features and capability and performance, but it's also the quality of the hardware itself. Okay. And then I'm going to just briefly talk about, and maybe this is too much detail, but I just want to briefly talk about the fact that one platform, that one SmartNIC platform supports all these port speeds, right? 10, 25, 40, 100 gigabit. And basically through a firmware change, right? So a software change. So we have we have a capture software that does 10 and 25. We have a capture software that does two ports of 40 and one that does 2 ports of 100. So it's very flexible. It can be done on the fly. And so this platform, like I said, supports all these speeds and all these different optics as well to monitor all different kinds of networks. Short range, long range, extended range transceivers we also support. And then for use cases where you can see this is a special kind of breakout fiber. Let me go to the next one, 8x10. So you can see that this card, you can do 8 ports of 10 gigabit. So this one card can simultaneously monitor 8 10 gigabit interfaces. And you do that using these fiber breakout cables and 40 gigabit transceivers. So it just shows you the flexibility of the hardware. It's one hardware platform, can do many different things because it's an FPGA. It can support many different port speeds, again, because of the FPGA capability. And then just one last slide here, and it's really just kind of a quick overview of who Napatech is and kind of what we've been doing for all these years. But we really pioneered the use of FPGAs for network and security monitoring applications many years ago, 15 years ago. And this is where our expertise in accelerating compute-intensive applications, right, on COT servers, right? This is our area of expertise, and this is where we've done all the innovation. So we have many patents, and we have many patents with IBM as well, joint patents. So, and when it comes to our vendors, once they start using our product, we're the preferred solution. And you can see these are some of our customers. We have a lot more that because of our non-disclosure agreements, we can't put their logos on this slide, but you can see customers like Facebook. They go out and they're monitoring all their networks using Napatech cards. They're 40 and 100 gigabit networks, and they're using tools like Suricata and Zeek to look for malicious activity on their network. And we are a public company on the Oslo Stock Exchange. Yeah, we're a Danish company, by the way. So that's pretty much the Napatech presentation. Looks like there's no more questions. Anybody have any questions, feel free to reach out to me. I'm Pete Sanders, and I run the field engineering team. And then DJ is my colleague who's on as well, and he's in charge of federal and North American sales. So he'd be happy to chat with you as well. Any final questions? If not, I'm going to turn it over to Mark from Axellio.
Hey Pete, just one last thing. We are a Danish company, but we work for Napatech Inc., which is a Delaware company in the U.S.
Yep. And the product's manufactured in the U.S. too. So.
Product is manufactured in Connecticut. Just a clarification there.
Okay.
So Mark,
Mark, it's all yours.
Yep. Thank you. Thanks, Peter. And really appreciate that discussion and kind of setting up my my presentation. So what I'm going to focus on is kind of how we use the Napatech technology in a use case for intrusion detection systems. Before I start, I'd also, actually like to thank Peter and DJ for inviting me along with SOSSEC and DCO for allowing us this time to present. Again, the primary purpose of this discussion will be to discuss how Axellio takes advantage of the Napatech technology to persist, index, and analyze pcap data with an intrusion detection system. Before I get into the use case itself, I think that just giving a little background about the company and how we got into this business would really help. So Axellio started out as a storage array company in the 90s. Our focus was on high-speed data input-output devices, basically enterprise-level storage arrays with very high reliability and durability required for enterprise applications. So that allowed us to develop a very specialized skill set around software and hardware that actually takes advantage very well of the technology for 100 gigabit ingest, which we'll discuss a little bit more. When we developed the storage array, our hardware was all very custom, and while we used some off-the-shelf products like the Intel processors and Seagate drives, most of the hardware we designed was custom and very proprietary. In 2015, we saw the value, obviously, as a storage company of non-volatile memory express, or NVMe. And I don't know if you guys are familiar with NVMe, but I'll talk a little bit about it and why it's important. We entered into a skunkworks project with Intel to demonstrate the value of NVMe versus SAS or SATA, which are both protocols, storage protocols that were essentially designed for hard disk drives. The product we designed, which we call Fabric Express, was actually based on primarily all COTS parts. And, there's multiple use cases for it. Again, today I'm going to focus on the pcap solution, but I want to kind of provide some context here. With the Napatech SmartNIC, we can actually capture 12.5 gigabytes of data per second. That's 100 gigabits, right? And from a storage perspective, that's a very heavy lift. One thing storage is really good at reading, but it kind of hates to write. So to be able to ingest at 100 gigabits consistently is very, very difficult.
Mark, just let me know when you want me to go to the next one, okay?
Okay. Yep. I'm still on the company intro, so.
Yep. Just let me know.
But anyway, from kind of a historical perspective, I can't help myself. The first storage product I sold in 1985 was an IBM 3380E, which was a 5.04 gigabyte device the size of a refrigerator. Two full strings of those devices was 41 gigabytes, and it cost about $1 million.
And if you think about capturing at 12.5 gigabytes of a second in 1985, that would have been a $1 million expenditure every 3 seconds. So pretty powerful stuff that we're able to accomplish today. I'm going to, again, focus on the combination of how our hardware and software can provide a substantially less complex environment for packet capture and security analytics. So now you can switch, Pete. So I'm going to give an overview of the what's called the FX2000, which is based on our Fabric Express technology. And just to define Fabric Express, what we've actually developed is the capability to have a highly switched PCIe fabric with between the servers on the Axellio Fabric Express product and the storage units or other PCIe version 3 cards that are located within the chassis. So again, the definition of FX is a highly switched Fabric Express environment. So we're on the specifications right now. So each 2000, FX2000 can hold up to 2 servers within the chassis, which is a 3U by 30-inch form factor. The servers are each dual socket and support Cascade Lake Xeon scalable processors from 28 cores down to 8 cores per CPU and supports up to 2 terabytes of memory per server. So there's a lot of processing power and memory that you can put in this 3U form factor. Each server board has a number of PCIe switches on them that, when connected to the switches on the internal storage boards or other PCIe compatible boards, creates a very flexible and highly optimized data flow machine. I will cover the flexibility aspect in another slide here briefly. The aggregate I/O bandwidth of the system, when fully configured, is 240 gigabytes per second. That is a big B, not a bits, that we're normally familiar with in the networking world. This is accomplished, again, by using dual-ported NVMe drives. Unlike SAS and SATA drives, which are storage protocols developed for the hard disk drives, as I mentioned before, the S stands for serial, NVMe is a parallel protocol designed specifically to take advantage of NAND memory, or the flash memory that you see in your typical flash drive these days. Thus, you can read and write IOs in parallel to these drives, creating an opportunity to take full advantage of our system, or the PCIe lanes in our system, I should say. Pete, what slide are we on? Yeah, I'm still good. I'm still on this. So the other piece, too, that I want to say is that the array can actually hold up to 72 NVMe drives, which is pretty substantial. And on the motherboard itself, you have a slot. That's where we put the Napatech card. So we assign a by 16 lane to that card because that is, the minimum number of lanes required for 12.5 gigabytes of transfer per second, or the 100 gig that they can capture and buffer for us. That 72 drives actually can translate at today's capacity of a 16 terabyte drive up to 1.1 petabytes of storage in that 3U chassis. So again, we pack a lot in a very small package. And all of this is commercially available, so it would be defined as COTS information. So go to slide 5, Pete. Or the next slide. This is a graphical representation of what, most servers look like in the world. Go back one, please, Pete.
Yeah, this is the right one. This is the right one right here, right? Yeah, maybe there's a delay. Is this the right one?
Yeah, that's the right one.
Okay.
Yeah, you're on it. So it's just comparing our architecture versus a traditional, just to kind of talk about it a little bit more. But you know, the representation you see here are, you know, kind of the traditional 1 or 2U devices that you see here. It could have a, you know, most of them have a SAS or SATA controller on them that connects to the PCIe lanes that then they put the drives behind those. There are some out there that actually have the capability to put NVMe drives on there, which are directly connected again to the PCIe lanes. And again, it depends on how the vendor bifurcates those PCIe lanes and assigns them to the various PCIe devices that allow them to actually achieve the bandwidth that they can get. And again, if you look at like your standard server, they're looking at 4 to 6 gigabytes per second. There may be some out there that are capable of achieving 12.5 like we can. But your standard server looks more like this versus the Fabric Express actually allows you to assign 160 lanes through the system and actually put additional type compute components on there like GPUs or TPUs or, you know, a Napatech FPGA. So in case you're thinking that 240 is overkill and there's probably not a lot of software to take advantage of that type of throughput, you're probably right. But having a lot of overhead allows Axellio to actually develop software that then takes advantage of what the Napatech card can provide, as well as provide a lot of functionality in that small package, which I'll get to in a little bit. So if you go to slide 6, Pete, this is just a picture of what a 2000 looks like. It's a front and back view of the system. The system on the left has 24 drives and 4 GPUs in there. The system on the right is the fully loaded drive configuration. Both servers here have two servers on them, and obviously the power supplies and the fans to be able to cool all that heat that's being generated from that. So go to the next slide then, Pete. Okay, this slide just talks about, if, looking at the picture that you saw before, this just kind of shows the different kind of board configurations that you can put into the unit. So again, 2 servers, but then you can have up to the 72 drives. So you can put 2 of these 24 by 2.5 SSD boards in there, or this kind of elongated 24 by 2.5 board in there, or multiple different types of either double wide, full height, full length cards, or full height, full length single wides in there. So a lot of the applications that we are working on are using, say, V100s from NVIDIA. So that's a type of flexibility that you can get. Additionally, just one more comment I want to make on this slide and about the flexibility is we can actually reprogram the lanes to even putting more cards on the motherboard itself. So if you had an application, like one application that we developed was a very high-speed video streaming application that required a bunch of standard NICs that were ingesting at 400 or 100 gig each, but 400 total on the board. So we just have a lot of flexibility as far as what we can do with the PCIe lanes themselves. So this essentially covers the hardware that we have that we've developed that provides the basis for what our pcap software in conjunction with the Napatech Smart NIC can provide. I see that there are no additional questions DJ, so I'm going to move on, but maybe I'll take a minute break and see if anybody has anything at this point about the hardware.
Mark, we had a late one come in after Pete finished, but we'll take that after you're done.
Okay. All right. So if you move to the next slide, Pete, this is just the transition into talking about the pcap solution. So if you move to this next slide, I just wanted to give you an overview. Pete did a great job up front of talking about what all the features and functions of what Napatech can do. In a standard environment today, most companies that want to do packet capture and recording actually employ some fairly expensive upfront equipment called tap aggregators, load balancers, or there's a couple other different names out there, packet brokers, to actually direct the packet flow to not only, say, a packet recorder, but to the IDS, in this case, IDS sensors that might be out there. And as Pete talked about, losing a packet is, obviously a very dangerous item, right? Because you just lose the capability to determine if you are getting attacked or have some kind of intrusion happening, right? So this equipment actually would potentially go to several recorders, because most recorders kind of max out at 40 gigabits a second as far as what they can capture, as well as multiple sensors, because those sensors also can't afford to lose packets, as Pete said. So, the flow that you see here is this, we'll call it a tap aggregator in this place, going to multiple pcap recorders and multiple sensors. Once an alert actually gets created from the, let's call it a Zeek server in this case, it actually gets sent to let's call it Splunk or Elastic SIM, and then the operator then will look at that alert and then request a network flow from the packet recorder to get the full story. So the criticality of scaling these sensors and the recorders to be able to have lossless packet capture is, I think, very complex and very expensive. So here's where if you go to the next slide, Pete, you will see that what we've done here, this is the FX pcap architecture. So, like Pete said, because the Napatech card provides so much functionality that you might see in a packet broker or a tap aggregator, like packet filtering and deduplication and those types of things, you potentially, with our solution, save a lot, and I'll take you through how that happens. So if you look at this blue box here, you'll see the logical representation of the Axellio chassis. So you see two light gray boxes there with boxes in there that represent server 1 and server 2. And then kind of in the lower right-hand corner there, you see kind of the disk farm, if you will. And again, remember, both servers are actually connected to the same disks and can read and write to those disks simultaneously. So what you'll see here is we've developed packet capture software that utilizes the functions that Pete talked about, like the distribution to multiple host buffers and intelligent multi-CPU distribution, along with the timestamping, filtering, and deduplication features that I talked before. We developed code that actually allows that to be persisted at a sustained rate of 100 gigabits per second with zero packet loss. At 12.5 gigabits per second, based on current capacities, we can store for about this packet data for about 24 hours. Of course, we know that most networks really don't ingest at 100 gig for 24 hours straight. They kind of burst up to it. But it's nice to know that you've got this kind of capability and can store your packets for further research down the road. While we're actually storing that, we're actually also indexing based on a 5-tuple and the timestamp for each packet, which is then stored in the farm. Simultaneously, storage server number 2 can provide what we call flow load balancing functions. What that means is we can actually feed either to an external server that you might see on the right-hand block there, or with a couple instances on server number 2 itself, the intrusion detection software. In most of our use cases, we're looking at Zeek and Snort and Suricata, kind of like Pete was talking about with Napatech. We use Red Hat actually as the operating system for both servers. And what the balancer does is it actually will feed, say, let's talk Zeek, either to like PF ring or AF packet, or another way that it accepts storage and data. And we can actually feed it at rates that it can handle, so that alerts can be sent and you don't have to worry about having multiple different instances of this out, because all the packets have been captured and it's fed into the tools based on the timestamp that was created at the receipt at the Napatech card. So it eliminates the need to over-provision your environment for the sensor side in order to make sure that you don't lose any packets and potentially get cyber attacked without your knowledge. So the other functions here is we do have the capability for flow send and a flow serve module that will, again, feed something like PF ring into Zeek or Snort on an external server. We also can feed to the log server from those pieces. And then, again, the standard piece here is that the operator can do the flow request, and that can be either a REST API or an SSH request or our proprietary flow read technology. So one of the advantages of this, again, because we're using NVMe drives and we have so much bandwidth, is I have talked to some operators in the field about how long it takes to do an investigation. And in most systems, most packet capture recorders, because the recording the packets is the primary task, it often takes a lot to get the packet flow that you're looking for. Because of our speed and bandwidth, we believe and have seen the capability to do those reads, that might take hours in a standard environment down to minutes. So, that could save a lot of time in the event of a cyber attack. So we believe, again, that this technology, this architecture, will actually, again, reduce the amount of footprint that you need, or swap C, as well as complexity. So the C on the swap C being cost, the second C being complexity. So with that said, we think that there's a lot of advantages to that. The other thing, too, I want to make sure that you understand is that again, because we can ingest such a high rate, one of the things you've got to be concerned about is actually what happens when you start running out of storage. So our FX pcap software actually allows the capability to do a circular first in, first out take on or deletion of the pcap data. However, if you did want to save that to another tier or into a SIM for longer retention periods, that can be redirected outside of the box as well. So again, all this is accomplished in a 3U environment, which can integrate into your, you can either be a brand new type environment, or you can integrate it into an existing environment using your existing IDS tools or SIM environments. And again, we think that this actually could eliminate the need for a lot of extra equipment like tap aggregators, servers for the sensors, and configuration work, maintenance, and cabling as well, as I said. So, Pete, I am done talking about that. So please go to slide 10. So slide 10 and 11, we're not going to spend that much time on, as I just took you through what all those functions are, but I wanted to leave them behind as an artifact. So Pete, if you go to slide 13, I'm sorry, go to the next slide. This is just a representation, we're getting toward the end of my time, but of the companies that we work with, from a front end. So you see Napatech on the slide regarding the hardware, Intel, NVIDIA, we've already discussed. It's not inclusive of everybody, but it's a good sample. And then some of the OEM software or open source software that we've implemented in other installations before. Again, the pcap software is commercial off-the-shelf available from Axellio. That's our own developed software. And then we work with multiple partners as well as customers to simplify their infrastructure because of the capabilities that we have in our hardware and software, minimize their cost and essentially increase their user performance. So if you go to the next slide, this is just a sample of some of the companies that we work with. I want to make a special note of Ceiling Tech in this. They are the ones that kind of helped us with this end-to-end intrusion detection architecture and some of the integration capabilities that we've developed around that. But, obviously, there's a bunch of recognizable names up there that we have worked for and with to help them accomplish goals around SWaP-C and increased performance as well. So that is all I have. If you go to the next slide, Pete. This is my contact information. If anybody wants to, has any more in-depth questions. And I would just, again, like to thank everyone for your time, and hopefully you found this helpful. If you do have any other questions, like I said, my contact information is right there. We have about a half an hour left to talk about the use case or any other questions you have for Napatech. So thank you very much.
Okay, well, thanks a lot.
Thank you.
Yep.
So Pete, there was a question that came in late from Brett S. Is HTTP2 decode supported?
Yeah, so what we do in the FPGA is we do up to layer 4 decode, some layer 5, but essentially that's the extent of what we do in hardware. But we do work with third-party DPI solutions that can do this HTTP2 decode. It's more of an application, more like an L7 decode. So, with like NTOP and their NDPI, and companies like Cosmos, they make a DPI engine. So we work with them, and we already have, integrations done. So typically, just, kind of an FYI on L7 is that, there's always new applications coming out. There's, it's a much more dynamic arena, and that's where, it's difficult to keep up in hardware. Even though it is a programmable device, it's still hardware, and, in the end, it still requires, hardware design. a hardware designer to go and design all the logic. So that's why we think that we do as much offload up front on basically up to L5, and then they take over from, after that. And then there's another question.
Yeah, Ed asked, is the Napatech virtual acceleration capability for data center available today? I'll take that one. It definitely is available today. We have a lead customer in APAC that is proving it as our, proving the functionality. They have been using the software for several months and have several cards as well. So definitely available today. I'd love to discuss your use case.
Okay, are there any more questions out there that people want to unmute and ask them? I'm happy to take them.
Yeah.
Okay, so I'm going to go to the last. This is Ed's slide, his last slide.
Pete, thanks very, very much. Pete, DJ, that was really good, outstanding information on the Napatech technologies and the cards. Mark, I'm really impressed to see a company like Xilleo, who is able to wield such a capability as Napatech has, and in such a robust and in an industrial way. Clearly. The needs at DCO, this fit very well into the needs of DCO. So I know we'll be seeing a lot of you guys around there quite a bit. Good luck with that. Let me just point out a couple things on this last slide for closing. A lot of people ask, what does COBRA mean? So it's Cyberspace Operations Broad Responsive Agreement, which is COBRA, which is a DCO ramp for their selection of a consortium, which is SOSSEC's OTA. And if anybody is not a member, the consortium is open to every type of company, whether it's an OEM or a prime contractor or a reseller. But when you join SOSSEC, COBRA is one of the OTAs. There are 6 more. A few at the Air Force, a few at the Army, and one over at NGA. So you're getting a pretty good selection of announcement activity from a broad suite of DoD and one intelligence agency. So just keep in mind, these are targeting non-traditional companies who are looking to bring a capability, ideally something innovative, into the DoD, and specifically in the case of DCO, it's really all about cyber. But as you can hear from today, there's a lot here to do with infrastructure, performance, and actually a prime capability in someone like an Axellio, who you can see has great experience. And so the opportunity to team with a prime like an Axellio, or to collaborate through this type of an event for innovation, is really the opportunity.